So folks, welcome. Once again, a very good morning, afternoon, evening, maybe night as well, depending on which part of the world we are logging in from. And welcome to the fourth installment of the MOU ILS series, which is the Mysteries of the Universe Institute lecture series over at the Indian Institute of Technology, Roorkee, India. We are so honored and delighted to have Professor Juan Maldacena with us today as our distinguished speaker. And as is customary, here's a brief introduction about Professor Maldacena. So he got his PhD in physics at Princeton under the supervision of Curtis Callan in '96, and I think he was appointed as an associate professor at Harvard the year after, and 2 years later he became a full professor at Harvard in '99. Since 2001, he's been a professor at the Institute of Advanced Study, Princeton. And in 2016, he became the first Carl P. Feinberg Professor of Theoretical Physics in the Institute's School of Natural Sciences. Anybody and all of us who have even a remote familiarity with theoretical physics have obviously heard of the ADS-CFT correspondence. So obviously, I mean, we are familiar with the fact that he has made path-breaking contributions to foundations of string theory, black holes. In fact, if not mistaken, his thesis was titled Black Holes in String Theory, and which is also, given the current context of the Nobel, which went this year, is a nod to the Nobel itself. And he has made so many contributions of course, in the area of gauge gravity duality, black holes and quantum gravity. And he has a whole host of awards and honors. I would just venture to go through a few of them. He was a recipient of the Alfred P. Sloan Foundation Fellowship in '98, the Packard Fellowship in Science and Engineering in '98, the MacArthur Fellowship again in '99, sorry. The UNESCO Hussein Prize for Young Scientists in '99, the Sackler Prize in 2000, the Xanthopoulos International Award for Research in Gravitational Physics in 2001, the Edward A. Boucher Award of the American Physical Society in 2004. He became a member of the American Academy of Arts and Sciences in 2007, a member of the National Academy of Sciences in 2013. He is a recipient of the Danny Heinemann Prize in 2007, the Dirac Medal of the International Center of Theoretical Physics in 2008, the Parmanchuk Prize in 2012, and he is a Fundamental Physics Laureate of 2012, the first batch of 2012 laureates. And he got the Diamond Konex Award as the most important scientist in the last decade in Argentina in 2013. He is a recipient of the Lorentz Medal in 2018, the Albert Einstein Medal in 2018, the Galileo Galilei Medal in 2019. So with that brief introduction, I humbly request Professor Maldacena to please give his lecture. Professor Maldacena.
Well, thank you very much for the very kind introduction. Can you hear me well?
Yes, absolutely.
Okay. So we'll be discussing black holes and the structure of the space-time. So here's a brief outline of the talk and a brief history of black holes. So we'll review how black holes were discovered in the context of general relativity. They were surprising, and people thought maybe they don't exist. But then it was realized that they are an unavoidable consequence of general relativity. And then they were so surprising that they were even not black. So Hawking discovered Hawking radiation, and we'll discuss that. And that perhaps they are incompatible with gravity, that they imply that quantum mechanics is incompatible with gravity. And then through developments in string theory, we will see that black holes, as seen from the outside, can be viewed as compatible with quantum mechanics. And this also will imply an interesting relationship between quantum mechanics and space-time geometry. But there are still several puzzles that remain with describing involving the interior of black holes. Okay, so let's start from the beginning. So we know since the times of Galileo that an observer traveling with constant velocity observes the same laws of physics as an observer at rest. So if we have two observers in two separate laboratories, and they're moving at constant velocity relative to each other, they'll every measurement will give the same answer, and they cannot tell who's moving and who is at rest. So now that was just Galilean relativity, and then Einstein continue with the same principle saying that two observers traveling with constant velocity observe the same laws of physics, but he added one more thing to the laws of physics, which is that there is a maximum velocity for propagation of signals, the speed of light, and that speed is the same as measured by both observers. So we have some light, and we have two observers that are measuring the same light wave. These two observers see the light going in at the same speed. I mean, naively, you would think that this one that is moving would see the light signal going slower. However, the way it works is that time for this observer travels a little more slowly, and distances are also contracted. And those two effects work in such a way that the speed that this observer sees is actually the same as the speed of light is the same for both observers. So the important thing is that it is possible to see the same speed thanks to the fact that time flows at different speed for the two observers. Now this gives rise to the famous twin paradox. So you have two twins that are born at some time, and then one of them travels, one of them stays at rest, and the other one travels very fast and returns. Then what happens is that the one that traveled very fast would be younger than the one that stayed at rest. Now you might say, you might wonder which of the two twins is the one that becomes younger, and that will be younger. And it turns out it's the twin that felt some acceleration. Okay, it was this twin. Now let's ask the following question. So suppose that we have a rule that says that when these two twins meet again, they would both die. Okay. Now, which twin would you rather be? Would you rather be the twin that stayed with constant velocity, or that stayed at rest, or the twin that felt some acceleration that was moving with variable velocity? I guess you probably are imagining that you would like to be this twin. Now, it turns out that the laws of physics are such that even elementary particles prefer this. So, and that's basically the reason why they move in straight lines. They try to maximize the time that they live. And so we have some space-time, and then particles classically move in sort of straight lines with constant velocity. And that's somehow the principle, sometimes called the principle of maximum proper time, or least action. Now, so the lesson of these developments is that space and time form, we can think of them as forming a single entity, which we now sometimes call space-time. And the time, how we measure time, depends on how we are moving, and especially with the velocity we have. So two observers that are moving relative to each other perceive time in a different way. And also particles move in straight lines to maximize their lifetime. So they move with constant velocity if there is no external force. Now we'll discuss something which is apparently different, which is gravity. So our intuition might lead us to think that heavier objects fall faster. However, since the times of Galileo, we know that everything falls in the same way once we remove the effects of air resistance. So if you throw a light or a heavy object from a building, and if there was no air, then both would fall in exactly the same way. Now, Einstein had what he called the happy thought. So he realized that when you fall freely, gravity disappears. So if you are if you are holding something in your hand, that something you're holding is heavy, but if you're falling together with the object that you're holding in your hand, the object will, the weight would disappear from this object. So gravity has the funny feature that if you're falling freely, it looks as if its main effects are disappearing. And he promoted this to a new sort of physics principle, sometimes called the equivalence principle, which this is just a name for this statement that when you're falling freely, it looks as if gravity is not present. So going with the flow is easier. So, and that's of course familiar from if something is in orbit, the person would feel that, the astronaut would feel that he or she is floating. Now, based on this idea, Einstein developed the theory of general relativity, which postulates that gravity is due to the geometry of space-time. And the idea is that a heavy object curves the space-time around it. So space-time is not flat, but can be curved, it can be deformed by heavy objects. And then when you have a particle that moves in that space, that particle follows the line that maximizes its lifetime. Okay, so it's like choosing the line of minimal length, but really what the particle is choosing is the particle of maximal lifetime. Now, let me just give you some examples of how gravity changes the flow of time. So imagine you have two observers who are in a building. So one is in the bottom part of the building. Let's say you are in the bottom part of the building and your friend is in the top part of the building. And each of you has a clock, and so you have identical clocks. And then you let these clocks run. And what you would see is that the clock that is in the bottom of the building would run more slowly than the one that is in the top of the building. Of course, here I've greatly exaggerated the effect. It's an effect of 1 part in 10 to the 15. It's a very tiny effect for an ordinary building here on the Earth. But it's nevertheless an effect that you can actually measure with very high precision clocks. So the best clocks that exist can detect the difference in height of 3 centimeters. Now we can have a similar twins paradox. So we have the two twins, and then when one of the twins gets near a very massive body and there is high gravity, this one will be younger. Okay. And again, it was the one that was feeling some high acceleration because it was not falling to the body, but staying on the surface, for example. Now, Karl Schwarzschild found the space-time geometry, and he found the space-time geometry outside the spherical body. And this geometry in particular tells us how time flows. So if we have a clock very far away, it will run at a certain speed. And then if you have a clock at the surface of the star, for example, it would run a little more slowly by a rate that is given by some aspect of the space-time geometry. So full space-time geometry in particular includes how time flows and what the difference is between the time on the surface and the time far away. So this geometry tells us the Schwarzschild geometry tells us the geometry outside a massive star, and it depends only on the mass of the star. The geometry inside the star depends on more details of the matter distribution inside the star and so on. And you can also find it, but we will not discuss it in detail. So if you make the star with the same mass, you make it smaller, then what you find is that that the geometry, of course, up to that point remains the same, and then it continues to be given by the Schwarzschild geometry. And time here runs even more slowly than before. And a person that is standing here would feel a larger weight. So if there is someone being held at the surface of the star, either with a rocket or in some other way, this person would feel a much larger weight than before. And then it turns out that there is a certain size for the star, which we now call the black hole radius. And if the star is smaller than this size, then there is something very curious that happens. A person sitting precisely at this location would feel an infinite weight, and also the time would seem to be frozen. It seems to not that this time seems not to run compared to the time at infinity. So this is a very funny feature, and it is this feature that led Einstein to think that these configurations were not possible, that perhaps they were the result of a mathematical idealization, such as thinking that the object or the star was spherically symmetric. But it was later understood that it was later understood that it was a generic prediction of general relativity, and I'll discuss that in more detail. But something important about these observers is that they are not falling freely. And you can ask what would happen if they were falling freely. And it turns out that if they fall freely, then the geometry actually continues behind this horizon. And not only that, but the observer that falls freely would fall through the horizon and would not feel anything special at the horizon. And the geometry continues inside, and inside the horizon, the geometry looks like a collapsing universe. So it's like a mini, Big Crunch, or it's a collapsing universe. And there is a singularity. The singularity is in your future, and for that reason, you cannot avoid falling into the singularity once you cross the horizon. It's like the singularity is like the end of time. So it's well, we don't know whether time continues beyond that, but at that point, singularity means that you cannot continue the evolution using Einstein's equations. So Einstein's equations become inapplicable near that point, and we would need to find a better theory to understand what happens. So you should think of the black hole as containing like a little mini Big Crunch universe inside. Now, one way to understand this, that some analogy that is often made, is the following. So we kind of view space-time as a river, and imagine that we have a river where the speed of water varies and becomes a little faster as you approach a waterfall. Then we can have some fish in this river, and the fish can swim at the maximal velocity, which will be analogous to the velocity of light. Okay, so as long as the velocity of the water is less than the velocity, this maximal velocity at which the fish can swim, the fish can swim upstream and avoid falling into the singularity. But as the speed of the water increases, it reaches a point where it becomes equal to the velocity at which the fish can swim. And at that point, a fish that is trying to swim upstream would actually remain stationary. And then if there was a fish in this region, even if it tries to swim upstream, it will end up at the waterfall or the singularity. However, if this water is, let's say, not transparent and the fish cannot see the sides of the banks of the river, then the fish has no way to tell whether they are remaining stationary or not. Of course, they can tell only their speed relative to the water. And this fish that is swimming here does not feel anything special. And if there is a fish swimming in the other direction, then that fish does not feel anything special at this point where the two speeds coincide. That's somewhat an analogy for the geometry of a space-time. So there are a few lessons that have been learned. One is that once you cross the horizon, you cannot get out. It was also understood that the star can collapse to a black hole, and that there are objects in the sky that seem to be black holes. So let me talk a bit about those. So how do we see black holes? So there are two types of black holes that are known to exist in the universe. Some are produced by the collapse of very massive stars, and their sizes range from 10 to 200 kilometers. And then there are black holes at the center of galaxies, and they are much bigger. They have a size of the order of the size of the solar system, the biggest ones. So how do we see them? Well, what typically happens is that matter falls in and it heats up and emits light or other radiation. So that's one way to see them. And another one is that sometimes we see the gravity waves that are produced when two black holes collide. Um, so there is a nice system that was imaged recently that that is the M87 galaxy. So that's some galaxy that is out there. And this galaxy was suspected to have a black hole because it had some jets of energetic particles coming out. So this appearing here in blue. Here it's the same picture, a bit more magnified. And then with some special radio telescopes, astrophysicists managed to make an image of the region very close to what would be the black hole horizon. So the black hole horizon would be, the black hole would be more or less this size here. And so you see the matter that surrounds the black hole, and the light is deformed and has a shape that is consistent with what you expect from with what you expect if you had matter orbiting a black hole. And many galaxies similar to ours have these very massive, supermassive black holes at the center. Yeah, maybe I should go back to the previous picture. So this black hole in M87 is roughly the size of the solar system. So the orbit of Pluto would be somewhere here, this size. Okay, and more recently, there was some more evidence. Well, over the last, let's say, 20 years, there was more and more evidence accumulating for the existence of a black hole at the center of our galaxy. And in particular, these two astronomers have measured the orbit of certain stars that are orbiting very close to the black hole. So the black hole would be a little dot here, and these are orbits of stars going around it. And just for comparison, this little dot here, that would be the size of the solar system. So the orbit of Pluto is this size here. And so these stars are relatively close to the black hole, and there is a very, they signal that there is a very compact object of the mass of order, the mass of 1 million times the mass of the sun. Yeah, through this evidence and then some other evidence, people are fairly convinced that there is this black hole at the center of the galaxy. And so, and for that reason, they gave them the Nobel Prize in 2020. And Roger Penrose is a theoretical physicist who really showed that black holes generically form. So remember that Einstein had his doubts on whether a black hole would or would not form when it's, let's say, not spherically symmetric. But Roger Penrose really showed mathematically that no matter, that under certain conditions, even if you perturb the black hole a little bit, if you perturb, let's say, the initial star a little bit, it will still collapse into a black hole. It will still collapse into a black hole. And he certainly proved many other theorems in general relativity about the properties of black holes. So we saw also that we see black holes when, if you have two black holes orbiting each other, and they slowly lose energy due to the emission of gravity waves, and eventually they collide with each other, emitting a big pulse of gravity waves that, and in 2016, we had the first detection of such pulses. And by now we have of the order of 50 or so detections of such collisions. Now, those were very interesting recent observational aspects of black holes. And certainly now we've entered a time where the study of black holes went from being something fairly theoretical to being to having a huge experimental component. In fact, there is a lot of excitement due to this very recent experimental and observational results for black holes. So the evidence for black holes has grown enormously. But I will not talk anymore about the experimental aspects. I will now continue talking about some other theoretical aspects of black holes. So the talk from now on is going to be just pure theory. And first, I'll start by discussing some interesting conceptual aspects of black holes. So black holes have interesting properties. So the first is that the final shape of a black hole is independent of how it formed. It's only characterized by its mass, its angular momentum, and in principle is charged, though black holes in nature, they are typically not charged. So stars can be all very different. They can have different chemical composition, they can have different color, they can be slightly deformed, they're not perhaps completely spherically symmetric, etc. But if they were to collapse to a black hole, if they all have the same initial mass, they would collapse to exactly the same black hole. And well, of course, it's also characterized by the angular momentum. But just up to these two numbers, the black hole geometry is completely fixed. Of course, those who know that these three pictures are three pictures of the same star. It's actually three pictures of the sun. But well, anyway. That's the first interesting feature of the black hole. The second interesting feature of a black hole is the following. So imagine we had one of those black hole collisions that we discussed. When the black holes collide, they form a bigger black hole, and bigger than each individual one. But the mass of the final black hole will be smaller than the sum of the masses of the initial black holes. And the reason is that the mass, of course, the total mass of the initial black hole is just the total initial energy. And part of the energy has been emitted into the energies of gravitational waves. And we can wonder whether there is any bound on the energy of gravitational waves that was emitted. And so Hawking asked himself this question, and he realized that there is actually a bound. So the total mass of the black hole can decrease. The final black hole can be less than the sum of the initial black holes, but the area of the horizon should always increase. So the area of the black hole horizon here has to be bigger than the sum of the two initial areas. And this prevents this black hole from having very tiny mass, because that would have very tiny area, and that's not possible. So you can show using the equations of general relativity that this property of the area is true. And this is a simple property of complicated equations, of the complicated equations of general relativity. So far we've discussed black holes according to Einstein's theory of general relativity, which is a classical theory. And when we include quantum mechanics, we find a new surprise. We find that black holes can emit thermal radiation. And this thermal radiation increases as the size of the black hole decreases. So we have a big black hole, such as the ones that exist in nature. They emit very tiny amount of radiation. As the size of the black hole decreases, it would emit more radiation. It will look, it looks hotter. And if it was sufficiently small, it might even look white and will emit even more radiation. So here are some temperatures for black holes of various masses. For a black hole of the mass of the sun, which are the smallest kinds of black holes that are formed naturally in the universe, this temperature is very, very, very tiny. So this is a number of degrees Kelvin, so degrees above absolute zero. So it's such a tiny temperature that we have no hope of actually seeing this. On the other hand, if you had a black hole which roughly has the mass of a continent, that black hole, if you were to collapse, it would have the size of roughly a bacterium. And since that size is, And that black hole will look white. So if we had this black hole and we were looking at it, it would be emitting a thermal radiation, and the temperature would be similar to the temperature of the sun and would look white. One way to, the Hawking formula says that the wavelength of radiation, of this thermal radiation, is comparable to the size of the black hole. So here, that's why this black hole has this size. That's the size of visible light. Anyway, now let me just briefly explain why we have this effect. So this is a qualitative explanation. First, this takes place in the context of the relativistic quantum mechanics. So in that theory, particles can be created and destroyed. And the vacuum itself is such that you could imagine having pairs always being pairs of particles, one with positive energy and one with negative energy, that are created and destroyed. But there is some principle that says that the only particles that can really exist should be the ones that have positive energy. So those are the real physical particles. However, if you wish, there is a policeman that enforces this condition, that energy should be positive. But these policemen are constrained by the Heisenberg uncertainty principle. So if this particle exists for a very short time, then the policeman cannot really measure its energy very precisely over that short time. And so it's allowed to have some negative energy, but only for a short time, and then it should immediately annihilate with the one that has positive energy. So in flat space, through this process, there is no net particle creation. Now, on the other hand, in the presence of the horizon, you can have again this process where the particles are created. But now, what happens is, due to the distortion of space-time, this particle has what the outside observer would call negative energy. But from the point of view of this interior policeman, that energy is not quite like energy. It's like more like momentum. And momentum can be positive or negative. So this policeman here has no problem with this negative energy particle, and certainly would allow this particle to exist. And for that reason, then this other particle can really escape to infinity, and we would see it as some positive energy flux from coming out from the black hole that makes the black hole disappear. What makes the black hole lose some mass. So we have some net particle creation. Now, this means that as a black hole emits radiation, it loses some mass, and the black hole therefore has a finite lifetime. And here are lifetimes of various black holes. So a black hole of the mass of the sun or the Earth will live much longer than the age of the universe. A black hole with an ordinary mass, let's say a mass of 100 kilograms, would evaporate in a tiny fraction of a second, very, very tiny fraction, and would be an explosion worse than a nuclear bomb. And a black hole of a mass of about a mountain, so that's 10 to the 12 kilograms, produced at the beginning of the Big Bang, would be evaporating right now. So those are examples of lifetimes. Now, we don't know whether these black holes were produced in the beginning of the Big Bang, probably not, but certainly they would be evaporating right now if they had been produced. And also there could be very small black holes produced in particle accelerators, but they would decay very quickly. And however, in the particle accelerator, this is something that could exist in principle, but in practice, none of this effect, this has not been seen. It's not a unique prediction of the theory. It can happen only under some special circumstances, such as having some extra dimensions and large extra dimensions and so on. And through the results of recent accelerators, they have not been seen yet. Now, this effect of the thermal aspects of black holes is very interesting, and it's interesting because it leads to some theoretical problems. And I'll try to explain now what these theoretical puzzles of black holes quantum mechanics are. So I'll discuss basically two puzzles. So one is why are black holes hot? And the other one is the problem of the loss of information. Now, when we have a system at finite temperature in physics, we think that the temperature is due to the motion of some microscopic constituents. And something that is hotter differs from something that is colder by the amount of motion you have in this microscopic constituent. So for example, for a gas, let's say the air in the room you're sitting, if it is hotter, then the molecules are moving very fast. If it is colder, they are moving more slowly. And we think that any temperature has an origin like this. And there is a related concept, the concept of entropy, which is basically counts the number of microscopic configurations. So for example, the number of configurations for those molecules inside the box. And the first law of thermodynamics gives us the entropy if we know the energy and temperature. And for the case of black holes, once we apply that law, we find that the entropy is equal to the area of the horizon divided by the Newton constant and h bar and so on. And so when you put in the numbers, this is the area in some units, which are very tiny. We call this Planck units. So for a macroscopic object or macroscopic black hole, this is a very, very, very large entropy. It's an entropy much larger than the entropy of any object of the same size. Now, an interesting aspect of this formula is that we can now interpret Hawking's area law in terms of the second law of thermodynamics. So the idea is that that increase of the area when black holes collide and so on can be viewed as enforcing or as a consequence of the second law of thermodynamics, which says that entropy increases. Now, so these are just some formulas that follow from thermodynamics, I mean, given the formula for the temperature. But we have the question of what are the constituents of a black hole. So they should be some microscopic constituents of space-time, and they are very universal. So we saw black holes are independent of the matter that forms them. In fact, we can even form black holes using gravity waves. So if we manage to concentrate some gravity waves over a small region in space, we could, in principle, form a black hole. So they don't depend on the details of matter. They only depend on properties of space-time. And so we think that understanding these constituents will tell us something about the nature and the structure and nature of space-time. If you wish, they are like the atoms or elementary pieces, elementary building blocks that make space-time itself. So that was one question. So the question of how the entropy of black holes arises. Then there is a second puzzle, which is the problem of information loss. So we saw that we can form black holes in many different ways, but they always evaporate in the same way. So we can send all kinds of information into a black hole. The information could be the type of star that formed the black hole, etc., or various particles we threw into the black hole. But as it evaporates, it emits apparently it emits thermal featureless radiation. And the question is how that information, what fell in, really comes out. What physical principles give that? Now, according to the principles of quantum mechanics, if you form an object in different ways, the quantum mechanical evolution is reversible. So in principle, that information still remains in the outgoing radiation, perhaps encoded in a very, very complicated way, but in principle, it exists. And so according to quantum mechanics, there should be some subtle differences in the outgoing radiation, which carry the information of how the black hole was made. Now, in order to answer some of these questions, we need a theory that puts together quantum mechanics and gravity. And one example of such a theory is string theory. Now, string theory is a theory that was developed since the late 60s. And you should think of it as a theory under construction. And its main claim to fame for our discussion is that it's a theory of quantum gravity. So it's a theory that describes the quantum mechanics of space-time itself. And it has the feature that it reduces to Einstein's theory under ordinary circumstances. That means low energies or long distances. And what is important for us is that it can describe in a complete way certain simple universes with negative curvature. It has some other features that we're not discussing that also make it interesting. But for our discussion today, we are going to focus on this special feature of giving some complete description of the quantum mechanics of certain universes. This is sometimes called holography. So it says that we can describe all the physics that happens in the interior of these curved universes in terms of a theory living at the boundary, so far away. Now, these are universes which have constant negative curvature. And so this is a picture drawn by Escher of a space with constant negative curvature, sometimes called the hyperbolic plane. So here, all these images have the same proper size, or the same size, but they are deformed because we are projecting that negatively curved space onto this two-dimensional flat screen, or flat surface. And when we do that projection, we can imagine this circle that lives very far away, and that's what we call the boundary. So some region that lives very far away. Now our universe doesn't have negative curvature if it has more like positive curvature. But we consider these universes because it is for these universes that we have a more complete description. So they are like toy models for systems with quantum gravity. And the nature of the description is roughly like this. So if we have, let's say, some particle moving inside this, this negatively curved universe, then that we can describe the physics in two ways. Either we have a particle that moves in the gravitational field. So the gravitational field in this universe is such that it attracts things to the center. And the motion, this particle can be described equivalently by the motion of some other particles that live on the boundary. These particles that live on the boundary are strongly interacting, and that's what I try to represent here with these particles that are moving in this funny way. So here we have very strongly interacting particles on the boundary. Now in this way, we can describe not only just some basic some simple particles in the interior, but in principle, we can also describe black holes in the interior. So even if we had a black hole in the interior, the black hole would be described by a very large number of particles here on the boundary. It should really look more like a fluid of particles completely filling the circle, but I have to confess that I was tired after making this many particles. So the temperature and entropy is due to the motion of these particles on the boundary. So we said that there should be some objects moving that give rise to the temperature and entropy of the black hole. And in this description, that motion, that entropy comes from the motion of these particles that have many different configurations on the boundary. Now, one other feature is that the theory on the boundary obeys the rules of quantum mechanics, and therefore so does the black hole in the interior. And if you accept this relationship between the anti-de Sitter, these negatively curved spaces and the boundary, then we find that black holes are consistent with quantum mechanics. So in this type of picture, we have a situation where we have something which sometimes it's called immersion geometry. So we have some system that lives purely on the boundary, and so that those were the particles that live on the boundary. And then we have a gravitational description that has one extra dimension. And we will try to explain how this works by a certain analogy. So I will call it a verbal analogy. So this is an analogy for trying to understand how this works. So let's imagine we have a sentence. So this is a particular sentence, a random sentence. So if a man does not keep pace with his companions, perhaps it's because he hears a different grammar. So that's just a sentence. Now, this is the same sentence. We can do an analysis, grammar analysis of this sentence. And we somehow implicitly did some analysis roughly like this when we understood the sentence. And so we can identify the various words. We can further identify bigger grammatical structures. So subject phrase, the verbal phrase, etc., and even bigger subclauses and so on. And then there are even some very long-range correlations between different words in this sentence. For example, man, his, and he are all related. And also this concept of keeping pace and grammar are also have some connection, some in the space of meaning. Okay, so the analogy is that the state of the quantum system on the boundary is analogous to a very, very, very long phrase. Okay, and the bulk spacetime characterizes the is something that is somehow analyzing the meaning of this very long phrase. So smaller structures here correspond to smaller structures here on the sentence or on the state of the system, and larger structures capture the structure of or the correlations present in this system at those longer scales. And particles moving in this spacetime also are related to further correlations that can exist between very long distance regions in that very complicated state. So that's one way we can think about this. So we can think of the extra dimension as somehow exploring the meaning of the quantum system. Now, what is a black hole in spacetime? Well, let's go back first to the sentence we discussed. So we have here a perfectly nice and formed sentence. And now we start changing some words. So imagine that we changed a few words. So we here changed the grammar for different, for lecture and he, and we replaced by she. And so we destroyed some of the long range correlations that we had. And the phrase can still be locally analyzed, so we can understand all the words and we understand part of the subclauses. But when we go to a certain level of understanding, the sentence somehow stops making sense, and we have a kind of horizon. So we cannot understand the sentence beyond a certain level because we lost those long distance correlations. If we continue making more changes, more random changes, then the sentence will start making less sense. So locally, it might make some sense, but at bigger distances it won't. So in that case, we would say that the black hole horizon is bigger, or that the black hole has grown. And if we completely put random letters, so we change all the letters, we would say that we have the biggest black hole. The black hole grew completely, and the area is characterizing the ignorance we have. And the fact that the area typically will grow is just saying that random changes on a sentence that made sense are more likely to mess up the sentence. And so that's the second law of thermodynamics, or this idea that the area will grow. Now imagine that all these changes were produced by a reversible algorithm. So imagine that they were produced by taking the original sentence and we applied these encryption algorithms, which for each initial sentence, it gives some sequence of letters. And if you don't know the algorithm, then it looks like a random sequence of letters. But if you knew the algorithm, then we can reverse it and recover the original sentence. So that's what it would mean to recover the information from a black hole. In other words, the laws of physics on the boundary are laws that change the state of the boundary theory, but they change it in a reversible way. They are analogous to an encryption process. And therefore, we can undo the formation of a black hole and, in principle, recover the original information. Now, I'll perhaps end by mentioning a few other features that have to do with the notion of entanglement. So the type of correlations we are talking about are correlations in quantum systems, and those correlations are called entanglement. It's a quantum mechanical property. It's sort of like correlations, like classical correlations like we had in the sentence, but they're in some sense a bit stronger. And we'll discuss one example where entanglement plays an important role in the geometry of spacetime. So we'll go back to the original Schwarzschild solution, so the black hole solution that Schwarzschild found. It turns out that that solution describes not one black hole, but two black holes. That's if you completely extend the solution across all the horizons. So it's a solution with no matter. And it can be represented by this figure, so where the vertical direction is time and the horizontal direction is the radial direction. And on each point, we have a two-dimensional sphere. And so the original coordinates, the original metric that space-time geometry that Schwarzschild wrote would describe the exterior of a black hole. But if you continue through the first horizon, then there's a second horizon, there's a second left exterior that looks exactly the same as the right exterior. So this is funny geometry, and it's the simplest spherically symmetric solution of pure Einstein gravity with no matter. It took many years to understand it properly, but that's the solution itself. Now, this is not the solution that would describe a black hole that forms in nature, because the black holes that form in nature are formed by the collapse of stars and there is matter and so on. This is some other geometry, and we could wonder what the meaning of this geometry is. In particular, we could imagine those two black holes to be very far from each other, and then they would be described by sort of, we have the two black hole exteriors, and then they are connected through the interior. So there are two black holes that are sharing a single interior. And as I said, if you find two black holes in nature produced by gravitational collapse, they are not described by this geometry. This is just some geometry. We are not discussing how we will form it. It's probably very difficult to form, but it's a possible geometry according to the equations. One might think that what this geometry is saying is that if we are outside one of these black holes at some small distance, let's say 1 meter from the horizon, and you have a friend that is 1 meter from the horizon of the other black hole, the distance through this geometry between you two would be 2 meters, even though the black holes might be far away. And this might make you think that perhaps you can use this as a kind of wormhole that allows you to travel between distant points, but it turns out that that cannot happen. So it is a time-dependent geometry, and so the fact that the interior here collapses implies that if you try to travel, so here these diagrams are such that lines that move at the speed of light move at lines of 45 degrees. So the fastest that you could travel is at the speed of light. And if you try to depart from here and travel to the left, you will end up at the singularity. And so despite sharing the interior and being relatively close at some instant in time, it is not possible to travel through this type of wormhole. So the idea is that in the exact theory, each black hole is described by a set of microstates, a set of, let's say, a gas group of particles or quantum systems that describe each of them. And the idea is that the wormhole, this wormhole geometry we discussed, is a particular entangled state. And as we said, entanglement is a form of correlation in quantum mechanics. So we have the fact that we can have a geometric connection from entanglement. So entangled systems, so these particular entangled systems, the entangled systems of the particles that make space-time, or the fundamental quantum degrees of freedom that make space-time, if they are correlated, they can create a geometric connection. Just going back to the analogy, just to make an analogy, again, we go to the phrases we discussed. So here we have a phrase, the original phrase we had in English, and now we take the same phrase and we write it in Spanish. So this is the same phrase, but in Spanish. And if you start analyzing this phrase, the particular letters are different in the two sentences. But when we start analyzing, they are different. But when we get to a certain level of analysis of the meaning of each word and so on, they have a common feature. And so we can think of that as a kind of wormhole that connects these two sentences in different languages to a common underlying meaning. And just to emphasize this, to emphasize what it would mean for the two black holes to share an interior, we'll tell you a little story. This is a science fiction story. So imagine that there were two people, let's call them Romeo and Juliet, and their families don't want them to meet, so they send them to separate galaxies, but they are very, very clever, and they they share entangled qubits, and they create two entangled black holes. And then if they manage to do that, then once after they created the two entangled black holes, they can jump into the black holes. And then these are the two black holes. And let's focus first on the bottom part of the picture here. And then they decide to jump into the black holes, and their families think, okay, they jumped into the black hole, they committed suicide, right? So that's the picture seen from the outside. Now, if according to the black hole geometry, now we focus here on the top part. When they jump into the black hole, they can meet here in the interior and live for some time here in the interior of the black hole. Eventually here they will also die when they go to the singularity. Okay, actually there are ways of rescuing them, but we will not discuss that. So the conclusions is that black holes are fascinating objects where the geometry of space-time is deformed in a dramatic way. Black holes and quantum mechanics give rise to interesting theoretical challenges, and string theory can describe black holes in a consistent way, at least seen from the outside. And space-time is an effective approximate concept which arises from more elementary particles living on the boundary of space-time. At least for certain spacetimes, these negatively curved spacetimes, we think this is true. And entanglement plays a crucial role in determining the structure of space-time. And for the future, I should mention that there remain many mysteries, including the meaning of the singularity, and we hope to elucidate them in some hopefully near future. There are also, one would like to extract lessons for cosmology. In cosmology also there is some initial singularity, and we would like to understand it properly, and we need really a theory of quantum gravity for describing that, and hopefully in the future we'll extract some lessons for cosmology from these theoretical developments. Okay, thank you.
All right, thank you so much, Professor Maldacena, for that incredible talk. That was obviously lovely. Thank you so much. Would it be okay if we take a few questions? Would that be all right?
Yeah, sure. Go ahead.
So there are two ways we can go about it. You can see that there are a lot of questions flowing in the chat. So maybe the one way is that you could kind of go through them and you can pick some that you feel like answering, or I could do that job for you. So whichever way you know, we could have a filtered set of questions, or you could have a look at them, and however it suits you.
Okay, why don't you look at them?
Yeah. Okay, let me do that.
Sure. While I'm answering one, you can look at the next one. So. Okay,
sure. So maybe I could read out. So there is a question by Mohan Agrawal. The question is that in light of recent theoretical developments in solving the black hole information paradox, do you have more clarity on the observational consequences of string theory?
No, so there's been recent progress in understanding how to calculate the entropy of Hawking radiation coming out of black holes. I didn't discuss that, but that was there were some interesting theoretical developments, and but unfortunately they don't allow us to make some measurable prediction. So all those the developments involve the measurement of a very sensitive observable, which is the von Neumann entropy, which is in principle measurable, but it's very difficult to measure in practice. So for any ordinary system, it might be that I think perhaps the best way to connect some of these ideas to experiment might be through some certain atomic physics problems, or maybe using quantum computers, that you can simulate these systems of strongly interacting particles, or actually build a system with those very strongly interacting particles that has a description that involves some kind of gravity. It won't be gravity in our 4 dimensions, but it might be some simple models of 2-dimensional gravity, for example. And there you can really do some experiments in a system whose description is well approximated by some theory of gravity. I think that's
Okay.
the best avenue to test some of the ideas that we were discussing today.
Okay. So there is another question by Gopal Yadav. The question is, according to the slowing down or the increasing of the flow of time, the speed of time, is there any critical value of gravity where time freezes?
Well, we saw that in a black hole situation. So when you have a horizon, it looks like the time, at least the time as measured by the outside observer, seems to freeze at the horizon. But we saw that the observer who falls in experiences an ordinary time. It's just what happens is that there is a huge difference between the two notions of time: the time measured by the outside observer relative to the time of the observer that falls in.
Okay. There is a question by Basavraj Kagali. It says, is there dark matter near the center of our galaxy?
Yeah, so the dark matter distribution, the dark matter does not interact very strongly either with our own matter or with itself. And so the galaxies are formed from some initial cosmological perturbation. So initially we have some uniform distribution of matter and dark matter, but then that distribution has some small perturbation. And then the galaxies form when that small perturbation collapses under the gravitational force. The dark matter distribution collapses, but it doesn't manage to lose all the initial kinetic energy it has, and it forms a big halo, much bigger than the size of the galaxy itself. So you get some we think that there is a continuous distribution of dark matter, which somehow peaks near the center, but it's not very, I mean, it doesn't go to infinity. Well, we think that the contribution from ordinary matter is more important near the center, because ordinary matter collides with itself and can heat up, lose energy, and collapse more effectively to the center of the galaxy. In fact, there's been no detection of dark matter, I mean, of the gravitational effects of dark matter near the center of the galaxy.
Okay.
So the detection of the effects of dark matter are seen most clearly when you go to the outer reaches of the galaxy, where the amount of ordinary matter is small, and then you can see the effects due to the dark matter.
Okay. There's a question by Aman Gupta. The question is, does quantum tunneling explain Hawking radiation?
Yeah, you can also view it as a kind of tunneling between the interior and the exterior black holes. It's somewhat equivalent to what the way I was discussing.
Okay. There's a question by Rishabh.
I should say perhaps I should say that there is the way you do the calculation is that you start from the fields. You start from quantum fields in the far past, and then you evolve them to the future in the presence of the matter that collapses to the black hole, and so on. And it's basically the stretching of space-time that produces some time-dependent background that creates these particles. And it's a well-defined quantum mechanical computation you can follow, and it's very similar to the effect that creates the fluctuations in the early universe. So we briefly discussed the fluctuations that seed the formation of the galaxies, and these fluctuations occurred in the very early universe when the universe was expanding very, very rapidly, according to the theory of inflation. And at those moments also there is a kind of cosmological horizon. And again, there is a similar effect that produces quantum fluctuations that produce then the primordial fluctuations in the density of the universe. So it's a calculation that is very similar. And the nice feature is that these fluctuations of the early universe are things we can see imprinted in the cosmic microwave background, for example. So all this, I want to point out that this Hawking radiation and the theory of initial fluctuations are two effects that are very intimately related. So even though we haven't observed directly the effect of Hawking radiation in black holes, we think that this type of effect is the best explanation we have today for the primordial fluctuations.
Okay. So there's a question by Rishabh Mehta. The question is simply, what is meant by black hole decay?
Yeah. So that means that the black hole will lose its mass. So the mass, it emits radiation and it starts losing its mass, and eventually it will, the black hole will disappear completely. So that's what it means for a black hole to decay. So in some sense, the initial black hole has decayed into radiation, to a bunch of massless particles, for example.
Okay, so there was a query by Dinesh Tarachandani. It says that in Hawking radiation, you explained that the particles will be released and antiparticles will be sucked inside the event horizon. Can it not be the other way around, that you have black holes which are sucking in the particles and releasing the antiparticles?
Yeah, so I did not talk about antiparticles. I talked about negative energy particles. So antiparticles means it's a particle with, well, it's a technical concept that means a particle with the opposite charge and properties as the particles, but the same energy. So for example, if we have an electron, the antiparticle is a positron, which has positive charge. Black hole can emit both particles and antiparticles, so in that sense. But both the particles and antiparticles it emits will have positive energy. So it cannot emit the negative energy particles. As we said, in flat space, we cannot have negative energy particles.
Okay. This is a slightly detailed or longish question. It says, what physical intuition was behind the ADS-CFT conjecture of yours? Like the Anderson-Higgs mechanism in high-energy physics was inspired by a similar mass gain phenomenon in superconductors. What were you inspired by while discovering the ADS-CFT correspondence? This is a question by Aditya Ravichandran.
Yeah, so the ADS-CFT correspondence came from thinking about the physics of some objects in string theory, which are called D-branes. They're a type of soliton, or if you wish, membrane, or could also be particle, that has a very precise description. Which was found by Joe Polchinski. They have two descriptions. So one is that if you have, let's say, one such object, it can be described by certain open strings. Its excitations can be described by open strings, and those open strings at low energies give some theory of particles. But on the other hand, if you have many of them, they can also curve space-time around them. And the idea was to relate these two descriptions. One was the quantum mechanical description, and the other one was the description in terms of a black hole or black brane, which was curving space-time. And the correspondence came from thinking that these two descriptions were equal. And it came by doing calculations in both, from both points of view, and seeing that they agreed with each other.
Okay. There is a question. So it says, what is the criterion for concluding that black holes are made up of small building blocks of space-time? It's a question by Stavros.
So could you repeat the beginning of the question again?
So the question is worded as, what is the criterion for concluding that black holes are made up of small building blocks of space-time?
Okay. Well, this is what we expect from Boltzmann. So that's not more than that. So Boltzmann told us that anything that has temperature is built out of something smaller that is moving. So I was calling that something building blocks of space-time, but it's not something concrete. So the one concrete picture we have for those come from this ADS-CFT correspondence, where we can describe the building blocks of the whole space-time with negative curvature in terms of particles on the boundary. I think probably we would like to get some better and better pictures for what these building blocks are. But we think that there should be some building blocks based on the idea that heat and entropy come from such building blocks.
Okay. I think this would be the final question. So there's a question by Manish Prasad. The question is, how does one understand the concept of a charged black hole? The association of mass and angular momentum has always made more sense to me meaning Manish, the person who asked the question, instead of associating charge with a black hole.
Well, in principle, the idea is that electric charge is conserved. So if you fall, if you have some collection of charged particles and you collapse them to a black hole, this charge still remains, and you have some electric flux coming out of the black hole. And so, well, and it makes sense. So it's something that follows from the equation, if you wish. So you have to modify your intuition so that you understand why this makes sense. And now the reason that normally they are not discussed is because the matter that the matter that exists in nature is quickly neutralized. So there can be currents that cancel the electric charges. So it's more like a dynamical reason why in our universe it's not so easy to make charged black holes, but that in principle they can exist.
Okay. Though I said that was the last question, there's a question which trickled in right at the end. And so that'll certainly be the last question. So there's a question by Deepan Betal, I think. And the question is, what role does a graviton play in mediating gravity if the space-time structure is purely determined by entanglement of boundary particles?
Yeah, so the graviton is related to the energy of these particles. So the fact that there is there are energy flows between these particles, and there can be energy transfer between the particles at the boundary, is related to the existence of a graviton in the interior.
Okay, so I think with that, maybe the team can unmute everybody, and we can have a round of applause for a beautiful talk by Professor Maldacena, and an equally nice Q&A session, though a brief one. Thank you so much.
Thank you, sir. Thank you so
much. So I guess that brings us to the conclusion of this installment of the Mysteries of the Universe lecture. And once again, thank you so much, Professor Maldacena. We really are very grateful, really appreciate it. Please stay safe. Have a good day.
Sure.
Bye-bye.
You too. Yeah, best wishes to everyone.
Thank you. Bye-bye.